So, good evening, everybody, and welcome to the British Computing Society Oxfordshire branch. I'm very pleased to welcome Paul Methven to talk to us today about nuclear fusion and the digital aspects. Those of you that have seen our website and the programme will have seen his biography, a long and illustrious career in the Navy, rising to Rear Admiral, awarded in the 2019 honours list as well. He's now turned his attention to working for UK Atomic Energy Authority and delivering the next commercially viable part of nuclear fusion. So without further ado, we'll hand over to you, Paul, and we're very excited about this talk. Thank you.
Thank you very much, Andrew, and good evening, everybody here and online. Yeah, so I was asked by Andrew to try and talk about digital and fusion, and the two things are absolutely symbiotic. So let me try and take you through a cook's tour of how I think digital capability can help deliver fusion. So a couple of caveats. Firstly, I am not a digital, whatever the single word digital means, expert. I'm not a fusion expert, although 18 months in, I'm learning. I'm a nuclear engineer, a traditional nuclear engineer by background, and I've got some expertise in major program delivery. So, so this is a practitioner's view rather than a computing or digital expert's view. So there may be some of you in the room or online who are A, digital experts, or B, fusion experts, or there may even be some who are in that Venn diagram overlap between the two, in which case, great. And there might even be some who add program delivery to that Venn diagram. And if anybody's got all those three things, please send me your CV now, because we're remarkably short of people that have got all of those elements of capability together, and we do need them. I'm briefly just going to skip over my previous world, and it's not for indulgence sake. The reason I do that is that with fusion, we don't yet have a product in service. But with where I've come from, and this is the artist's impression of Dreadnought, which was one of the major programs that I led in my last role in the MOD, we have seen the full life cycle, right from the early stage of design through to in-service operations and indeed decommissioning. And through that, we begin to understand actually how data is essential to support the totality of that life cycle. So there are complex engineering endeavors where we can see what the whole story looks like and learn from in order to bring back into the very front end of making fusion a commercial reality. So data is at the heart of delivering a project like that. And it's also, of course, at the heart of the operational capability there that those boats supply. So you need huge amounts of computing power in various aspects and huge amounts of modeling capability to design one of these things. Then it gets even harder when you try and build. This is a photograph from inside the Devonshire Dock Hall in Barrow with 2 attack submarines in build. Some years ago now, things have moved from there. So conceiving of things and designing them is hard. Building them is even harder, because all of these problems that you come across in build, you then need to solve really quickly. And in order to be able to do that, you need to understand the design intent and go back to how you've captured that in order to solve those problems, as the US colleagues would say, on the deck plate, what we call manufacturing engineering. And then the problem gets even worse in your in-service when you have to maintain these things. So that is an aerial shot of 9 Dock in Devonport, where we refit nuclear submarines. And not only do you need to understand all of the components of data about the platform, the submarine itself, you need to understand all of that about the facilities within which it sits and the interaction between those facilities that you conduct the maintenance with and the asset on which you're maintaining. So that data management and digital thread challenge is even bigger. And then when you bring it all back out into operations again, you need to rely on that understanding in order to make it work. So there are these programs that we can learn from about how to properly exploit digital capability and translate this back into fusion. So that's sort of my background. Now, it's really dangerous doing this somewhere like Oxford, because you probably run the risk of several PhDs in front of you saying, yes, well, we know all this and you've got this wrong. So, but I've been guilty of making assumptions about audiences before. So just to get us all on the same page, what on earth is this fusion thing and why does it matter? So we talk about glibly bottling the sun. And it's probably important to talk about the sun and the stars, actually, because the first point is that fusion as a process is demonstrated by virtue of the fact that it is precisely what powers all of the stars. So we know that fusion works. And what we're really trying to talk about in fusion energy is replicating some of that core process in the Earth, on the Earth, but by different means. So here, the mechanism that causes fusion to occur is supported by the mass of the sun, i.e. the gravitational force that it applies to some atoms, or ions actually, atoms stripped of their electrons, to get them to fuse. That overcomes the repulsive force, the Coulomb force between those ions. We don't have that benefit of recreating the gravitational mass of the sun on Earth, so we have to find another way of doing this. And the first thing to look at here is we take two particular variants of hydrogen in this particular type of fusion we undertake at Culham, called magnetic confinement fusion. So we take what's called heavy hydrogen, so deuterium, and we take very heavy hydrogen, tritium, and we force them together by virtue of heating them to very high temperatures or energies, about 10 times hotter than the center of the sun. So temperature equivalent would be something like 150 million Celsius, which sounds bonkers, and in some ways is. But at those energy levels, they're able to collide and overcome that Coulomb repulsive force and fuse. And in doing so, they release a significant amount of energy. This is, of course, really precisely the opposite process from fission that powers the things I showed you earlier, where you're taking very heavy atoms and splitting them, releasing energy that way. So the energy levels here are broadly about 20% of the energy that's released is in helium, so inert gas, but about 80% of the energy is in neutrons, very, very high energy neutrons. So if the scientists among you, 14.1 mega electron volts of those neutrons, and a lot of them in an operational fusion device. So does it actually work on Earth? Well, I'm sure living here, you'd be well aware of the record that was set at Culham in the jet facility actually just prior to Christmas and announced just afterwards. And here, that pulse. So that works, and that particular pulse released 59 megajoules of energy. I think the press quote was about 60 kettles of boiling. Doesn't sound hugely impressive, but don't worry about that, because the time span of that pulse is just limited by the heating of the magnets, because that device was designed and built in the 80s, or designed in the 70s, built in the 80s. So it does work. So a little bit more detail, how do we get that to operate? So I'm going to talk about magnetic confinement fusion. There are other ways of doing this, but at Culham, what we do is focus on this. So we take this hot gas of deuterium and tritium. As I say, we heat it up to about 150 million Celsius or 150 million Kelvin. There's only a small difference between them at that size. And you've got fusion, okay? Much harder to do than to say, but we've got to confine, levitate, if you like, that plasma. And we do that through these magnetic fields. So there's huge magnetic fields actually off the coils, potentially in power generating devices up to around 20 Tesla. So that's an enormous amount of magnetic field force. And then we shape the plasma with coils in other directions to provide stability and control it. And just to think about the forces we're talking about here, this is one half of this device, so that's replicated on the other half that goes round in the donut like this. And down the middle, there's a massive great solenoid. And the solenoid and the next experimental facility in ITER, as actually, if you were to sustain its magnetic pulse, is capable of lifting an aircraft carrier. So the magnetic forces are quite extraordinary here. The loads that are transferred are quite extraordinary. And we've got to model all of this. So begin to think about the multidimensional nature of the problem. The device that wraps around all this, we call a tokamak. It's a Russian acronym, basically, for a magnetic confinement chamber. This is actually a picture of mast upgrade, mega amp spherical tokamak upgrade at Cullen, our newer experimental facility. And there's the major components of that. So you have a vacuum vessel, beam tin shaped in this particular type of device, a solenoid down the middle which provides a magnetic impulse, what we call toroidal field coils that primarily confine the plasma, those pink rectangular limbs around the outside, poloidal field coils that wrap around the other way to stop the plasma sort of shooting outwards out of the machine and to shape it. And then this funny little thing at the bottom called a diverter, which turns out to be hugely important because the amount of heat flux you're talking about inside the device there eventually needs to be channeled somewhere. And you need to contain and confine and channel that heat in a very, very clever way. And that's what that device actually helps us to do. So far, so good, right? Broadly, that's how we do fusion. So that's what it is, but like, why do we need to do it? And it may seem an obvious question, but it is, I think, worth asking and answering, because actually of the level of expense that we're going to have to go to make this work. So my summary of why we do this is global problem, national opportunity. So here's the first of 3 slides that just set the problem in context. This is Florida fires 2 or 3 years ago. And the slide's worth looking at for a couple of reasons. So firstly, the rank unacceptability of what's going on the slide. I don't mean golf. I mean, some people would say golf is unacceptable, but that's a matter of opinion. But the unacceptability is clearly the fires in the background. But the bit in the foreground is interesting because it's a normalization of behavior. It's as if people are saying, well, that is now normal, so we'll just carry on playing golf. And we're not waking up to the scale of the problem. You know, here's another look at it. So park for a minute the impact on the planet in terms of long-term climate change and just look at the particulate effect and the causes and effects on health. So there's 2 very well-renowned publications which put annual death rates globally at somewhere between just over 4 and close to 9 million per year, just from fossil fuel burning. So if I just say that broadly, estimates of the number of people globally killed by COVID is around 6 million, we are doing more than that every single year just by virtue of fossil fuel burning, without thinking about the subsequent long-term impact on the planet. And isn't it interesting, because the level of effort that we put into tackling COVID, and of course we should have done, just shows that sometimes when the problem is very proximate to you, you take action, but when the problem seems distant to you, you don't. So the action is driven by the proximity of the problem rather than the level of impact. Human behavior. So let's do another look at contextualizing the problem here. So this is the rate of increase in fossil fuel and other energy source consumption up until 2020. And what we're looking at on the y-axis is conversion of all those energy sources into what we call megaton or gigaton equivalent of oil. So if you kind of converted the calorific value of oil, you get an equivalent basis here. And you can see, of course, that if you stack up the first three waves there, you get to sort of plus 80% of global energy demand supported by fossil fuel burning. The first thing to note is actually the continued increase in coal. So despite the fact we've been talking about climate change for a hell of a long time, we've continued to increase coal burning, and some nations continue to do so. So that's point one. The second is just look at the steepness of that curve. So that goes to 2020. The shape of that graph is not changing. And when you consider that broadly on average, although we're in a bit of a funny world at the moment, GDP globally is going to continue to go up, and GDP is of course correlated to this, and global population is going to rise by approximately another 3 billion by 2100. The scale of this challenge is getting enormous. But don't worry, we've signed the COP26 agreement, and surely we'll be at net zero by 2050. Well, honestly, what does it take to do that globally? By the way, we're doing quite well in the UK. So here's a bit of maths that Ian Chapman at UKAEA did just to ram home the point. So on the graph on the left, that is about 11,000 megatons of oil equivalent, 11 gigatons of oil that we utilize on a daily basis. You've got to get rid of all that. And broadly speaking, there are 11,000 days there were from 2020 until 2050. So if you have to displace 11,000 megatons of oil equivalent in 11,000 days, that's kind of one a day. And what does that mean in energy production? Well, a megaton equivalent of oil is about a Sizewell B nuclear power station's output, or a Hornsea wind farm output. So if globally you've got to build and start producing one of those per day, every day for the next 30 years, just to displace the energy demand that you see on the left, without even considering what's going to happen between now and 2050 and then beyond, you begin to get a sense of the scale of the problem. And to do that would take about 4% of global GDP, which doesn't seem unreasonable given the benefit, but we're just not doing it. So, and more than that, I don't think we can. We're going to need additional sources of energy to solve this problem. So sorry for the scary bit, but it is important to get the context. One could do a lot worse than take advice on science policy from Stephen Hawking, and this is the on the last page of his posthumously published last book. So what world-changing idea, small or big, would you like to see implemented by humanity? And his answer was, this is easy, fusion energy. So that's why we should do it. And we are incredibly well placed in the UK to lead that by virtue of the experience at Culham in actually operating fusion plant. So how are we going to do it? Well, the first thing to say is the UK government, and I'll probably get into trouble for this, but for once has actually got a proper strategic view on something. And in this space of fusion, it has published a genuine strategy. And that's it. It's only a short read, actually. It's worth picking up. And the strategy is really to say the problem needs solving. That's the global demand. And we, the UK, are incredibly well placed to solve it. There's some hyperbolic language, of course, about science superpower, but in reality, the guts of it are this. Goal one, demonstrate commercial viability by actually building a prototype that actually gets more energy out than you put in. And goal two, which is really important, in doing so, stimulate an industry globally and make sure the UK is actually world leading in it. And effectively, those two goals set the headmark for the programme that we've launched at UKAEA Quad Step. So that's the demand signal. And basically the strategy has these three dimensions to support the goals. It says, look, international leadership, is it possible? Science and technology leadership, is it practical? And then commercial leadership. So briefly, sure, it's possible. Well, it is possible. I showed you the pulse from JET. That is actually the JET device that generated that pulse. Somewhere in there is that chamber that contains the plasma. And it's a pretty big device. We'll need to go much bigger in terms of operating plant, but it's hugely complex. But that was an incredible piece of engineering conceived in the late 70s, built and commissioned through the 80s. Incredible foresight from some of the engineers that put it together. So we can do it, and we've got the experience of operations, which allows us to have the experience to design. So that's the kind of science leadership there. We've got to show it's practical, though, energy scale. And if you just upscaled that jet device, you'd struggle a bit. So some clever folk at UKAEA some years ago had this concept of changing the architecture of the device. And fundamentally what they said is, look, this is all about confining the plasma through magnetic fields. But the magnetic field drops off pretty rapidly, so it's 1 over the radius away from it. So the closer you can put that plasma to the magnetic field, the more effect it has. And actually what you can really do is have less magnetic field. So less magnetic field, less cost of magnets, less cost of buildings and support, because even the support structures are amazingly strong for these things. So can we architect the machine in a cleverer way in order to drop the cost of it and get close to something that's relevant commercially? So the basis of that is this plant at Culham, mast upgrade, incredible little piece of engineering. But when you squash this plasma into a smaller box to take advantage of the architecture to reduce the magnetic field, you end up with this 150 million Celsius in a smaller box, and you've got to get rid of that heat somehow. So this device has this very clever bottom end.
Yeah, the microphones are there. Do you want me to give you a laser pointer?
Oh no, that's okay. I'll stay static, or I'll just employ a good old fashioned projection. So we have to exhaust the heat, and we've come up with a way of doing that. And to just get back to a bit of this modeling and digital that underpins the design for a minute. Sorry, there's a picture of the outside of the machine, which won the Royal Academy for Engineering Major Projects Award last year. To get back to some of the ways in which digital and modeling capability interface with the science to allow us to make these leaps, here's one example. So don't worry too much about the conventional and Super X, but the exhausting of heat previously would give you a very, very narrow spike of heat that you had to deal with. So if you look at that red curve at the top and the distance at the bottom, just over the distance of a few millimeters, you've got an incredible heat flux, which would melt your device if you then went to power station levels of heat. So you've got to find a way of dropping that peak heat flux in order to manage it. So about 10 years ago, the design was conceived and these predictions were made as to the amount that peak heat flux would drop. And those are real results from about 18 months ago in the operation of that device. So rarely do you do 10 times better in any field. If you can, that's amazing. But also if you want to see modeling match reality or reality match modeling, you can't do much better than this. So this gives us confidence of two things. One, the solution works, but also more importantly, that the predictive and modeling capability that sits behind this also works. Therefore, we've got some increased confidence that we can take that forward into future devices. So at the heart of all this is the ability to conceive of things, to represent them in some digital way, to model their outcomes, and then to use that to evolve the design further. But we've got to take this and make it practical. So that's what we aim to do with STEP. And this is the mission for the STEP program, Spherical Tokamak for Energy Production, which is to very audaciously deliver a UK prototype plant targeting around 2040. And importantly, a path to commercial viability of fusion. And we actually start with that last bit, which is, while so far the experimentation has worked, as I would put it, left to right. So what problems do we have? Let's try and solve that one, the next one, then the next one. The program we're running now starts from the other end of the telescope and says, where do we actually need to get to? What do you really need to make a commercial fusion plant viable? Well, let's set that as the design target and drive the program that way around and try and let the science left to right meet the demand of commercial right to left. So pretty daunting mission, but hugely exciting. So with the science and the engineering, we then need to add some other factors to make this work. We need to launch a major infrastructure and regeneration and delivery program. That picture there is of the ITER facility in the south of France, the International Thermonuclear Experimental Reactor, so the largest international science collaboration project anywhere in the world. And effectively, that is taking the JET device that I spoke about earlier that set the world record and going to the next stage. That will first become operational in the late 20s, early 30s. But you get some sense of the scale of the infrastructure program there. So that building in the center is something like 80 meters across, about 120 lengthways and about 80 high, with enormous switchgear and electrical distribution at one end of the site. So to get fusion energy to work, you know, it's a pretty big program in terms of the infrastructure. I would argue that to do this in the UK and to go further than this device is going, which is what our aim is, we're much more in the territory of this. So if you keep up with other programs in the UK, this is a fairly recent slide from Hinkley Point C, currently the largest, I think, infrastructure program in the UK. So we're on this sort of scale here in terms of program delivery. So we've got all these scientific challenges, and I'll come back to some of them. Plus we've got an incredibly mega infrastructure delivery challenge. Just to go back to ITER a minute, it's a major manufacturing program. So here inside the ITER facility are two segments of what we call the vacuum vessel. So if you can imagine those replicated and they form a ring donut. You can clearly see people in there. That is 60 meters circumferentially, welded, as it turns out, to a tolerance of 1.4 millimeters. So that the quality of the engineering, the scale of the engineering required, the scale of the infrastructure is quite eye-watering. And if you think that all of this needs to be designed, conceived, managed effectively through build, then into operations, and then into in-service, that is a huge data management problem. So we're trying to learn some lessons from this. And we're trying to learn some lessons from other complex mega programs. There's a few. Top left was the one I ran. Bottom right I'm very familiar with. The Queen just opened the bottom left earlier in the week. And Heathrow Terminal 5, you can see. And I put the vaccine program on there quite deliberately. I was talking about this with a couple of you in the preamble. That we've slightly, unfortunately, in the world of major program delivery, fallen into a paradigm where everything takes a hell of a long time. But it doesn't need to. So the top left program, we basically had a design to delivery timeline of about 26 years. But if I go back to the 60s, when we did it the first time around, it was 6.5 years. And the vaccine program shows what can be done if you put the national will behind it and you get on with decision making and you empower people. So it is possible to do these things really effectively. But the scale of what we're trying to do is not just a one-off program. Really, in my view, it's of this sort of scale. That is Calder Hall. That is the UK's first civil nuclear power station, I think online in 1957. And of course, done quite quickly in those days. And then that spawned 18 power stations thereafter. And we're talking about the start of a new industry here. So it's as big as Hinkley Point C, but with the aim of then moving to commercialization thereafter. So we have to think about the whole program, not just as a one-off, but about replication and deployment. And the reason we need to do that is if we don't get that technology globally deployed, we don't make inroads to the climate challenge. But it's a big bet. It's really uncertain. There's lots of risk in it. I'd argue that the risk of doing nothing is much bigger. But to be honest, it is risky. And we've got this tricky little problem in fusion, which is that the gap between an experimental device and a power plant really can't be filled. You've pretty much got to go for it because there's a certain scale of plant you need to get more energy out than you put in. And fiddling around in the interspace doesn't really allow you to solve the integrated design challenge. I'll go through in a minute some of the discrete problems that fusion brings rise to, but the biggest one is trying to solve every single one of those simultaneously. So what technically are we aiming for in the program? Well, if we go down the right-hand side of this, we're aiming to produce a prototype that confidently demonstrates, not much, but confidently demonstrates 100 megawatts electric on the grid. I think we'll do better than that, but we've got to be confident. It's got to sustain its own fuel supply. So if you go way back to the start, and I said we had deuterium and tritium. Deuterium's easy, comes from seawater. Tritium we breed from lithium because tritium is not naturally occurring. It has a radioactive half-life of 12.3 years, so it's all naturally decayed away. So we have to breed it. So we have to make sure the machine that you put lithium in can breed its own fuel supply. You also have to make sure it's maintainable, because a power station that is broken all the time or in maintenance all the time is not a commercial proposition. So unlike an experimental device, you need to design one thinking about the availability target. So that's maintainability, outages, reliability of components and integrated systems, and of course the longevity of materials. And we've got to do this whilst ensuring that it's safe, that has a minimum environmental impact, because we're actually trying to save the planet, not kill it, that we do that manageably and repeatedly in terms of cost. We do that in terms of schedule. And a really high level outline of the timeline we're looking at is here. And we aim to get into commissioning and operations of that prototype around 2040. We're working on the detail of this. There's loads of uncertainty and risk, but that's broadly where we are. By the end of, by about 2 years' time, we will transition into a completely different phase of the program where we really partner with industry to deliver. And we're going to end up setting up a new company to do that, we think, waiting for government permission to do it, and really bring industry together so that it's not just the amazing science that goes on at UK AEA, it's the weight of industry added to that to solve these challenges. And very excitingly, we've got to put it somewhere. So we ran a nominations process, and we invited nominations from anywhere in the country, and we got 15 really high quality nominations, which we evaluated and reduced to 5 on a shortlist, which are ringed there in green. We have now made a recommendation to Kwasi Kwarteng about which site we should go for from those 5. And when he makes a final decision on that, which I think will be fairly soon, we'll get an announcement by the end of this year, and then we're into all of the things that are on the list. So Fusion will have a new site that will be known worldwide, and we'll move into a different phase of delivery in the program. So that's a really exciting piece at the moment. So when people say it's coming, it really is. But you know, it's still bloody hard. So why is it so hard? Do you know how it works now? So what are the challenges of it? Well, the first challenge is trying to get up to this integrated power plant stage. And the integration challenge is just enormous, because you've got to integrate a plant that individually and collectively solves the following challenges. So challenge 1 that comes through here is getting the fuel hot enough. So we've got to heat that fuel mix of deuterium and tritium in the center of the plasma, and the middle bit that you can't see, that's non-visible, is the hottest bit. You've got to get that to 150 million Celsius. So you've got to heat up this deuteron, this deuterium atom or ion. You've got to heat up the triton, and you've got to slam them together. So getting that energy in there to heat them up and produce a helium ion and a neutron is the first challenge. So energy in is a huge challenge. But you produce all these neutrons, which is what you want to do, because that's where the heat comes from. But you don't get something for nothing in fusion. So all those neutrons then cause problem 2, which is that they damage the structure. So there's the microstructure or a lattice and steel or tungsten or whatever that's surrounding the device. And they dislocate the atoms in there, they displace, they cause all sorts of challenges, some of which we don't really fully understand at the moment. But we have to manage that. So you've got to heat it up and you've got to manage the neutron damage. And then you've got to get rid of the extreme heat. So the plasma, as I say, at the center of it is incredibly hot, but just on the other side of that vacuum vessel, you're cooled down to about 20 Kelvin. So you've got an enormous temperature gradient to deal with, and you've got to get rid of this heat out of the diverter. So you've got to exhaust that heat without melting the device walls. So the engineering challenge here, as well as the science challenge, is massive. You then have to breed that fuel. So the neutron impacts the lithium, the breeding blanket. So here we are, a representation of lithium. Neutrons hit that, and they then produce tritium ions. But you've got to take that out of the machine. You've got to go through a chemical process plant. You've then got to extract that tritium, get it in a usable form again, and then pump it back into the machine. So you have a huge chemical process loop going on in real time through this. And here are your frozen pellets of tritium that you're going to fire in the machine like putting wood on the fire. So there's only about 10 seconds worth of fuel in a fusion reactor, unlike years worth of fuel in a fission reactor. But you're going to keep firing that in there and process that in real time and keep up with yourself. And then you get to the last problem, which is that all those neutrons give you lots of problems, but one of the problems they give you is that we do activate, make the machine radioactive. It's not fissile, so you can't have a meltdown accident, but it gets what we call hot. So you can't put people in to maintain it, so you have to do it by robots. So here is a robotic arm inside the jet facility, and you need robots to do it because you can't put people in there, so you need to design the machine around robotics. So there's a huge robotics component to this as well. So pretty hard. Oops. But if that wasn't enough, if you think about the data aspect of this, it's highly nonlinear. So big machines have different physics to small machines. So the extrapolation is hard. Those neutron effects actually change the diagnostics and control. So some of the things that you use to sense in a smaller machine, you can't use to sense in a larger machine, they just get swamped. There's massive uncertainties individually in any part of this problem and in aggregate. So it's what I could describe as the mother of all uncertainty quantification, UQ problems. We're trying to develop the modeling capability for each individual bit and in aggregate as we develop the design. So it's a concurrency problem writ large. There will be, as we go forward, a huge high performance computing demand when we start running integrated models and trying to do them pretty fast. And the simulation we have to deal with is multi-scale. So, one of my team put this together to show that we're trying to model from the nanoscale in material terms right up to the large scale in terms of the way the machine reacts with some of those forces that are big enough magnetically to lift an aircraft carrier. So what's the neutron displacement at the nanoscale? What's the FEA impact, modeled impact at that top scale? And we need some degree of integration of that data stream and translation of that modeling capability. So it's pretty eye-watering. So how can digital capability help? Well, I think probably in three main phases. So if I take that timeline I showed for the program earlier on and just overlay some boxes on that, the first way it can help is enabling design choices. By being able to exploit digital capability, we can support the design choices. The second way is really what we would call digital thread, which is capturing that design. And then the third way, when we get closer to the end, is simulating in aggregate the performance of the entire system of systems. So to kind of take these in turn, to enable the design choice, we need multiple models to evaluate all the individual parameters, all of the forces, all of the computational fluid dynamics, all of the plasma modeling, the whole lot, multiple models. And we need to simulate dynamic performance. So it's not just statics. Most of the challenges here come in dynamic. Digital capability gives us an amazing opportunity to sort out spatial design. Trying to cram in all of the stuff we need in some incredibly tight spaces here is a real spatial management challenge. So simply being able to model that effectively in CAD systems and then represent that through into manufacturing is really important. And particularly a thing that caught us really hard in submarines and would be a problem here is tolerance stack up. So you just really need to be able to manage tolerances from one part of the machine to another, particularly when you're heating them up and cooling them down at such extreme rates and ranges. And if you know all this, then downstream operability and maintainability can be improved. So it enables design choice and development. It doesn't give you the answer, but it gives you some insights to the answer. Once you've got an answer and you're then developing that, then you need to be able to support that through life. So I would talk here about capturing the product properly, managing that information and understanding the decisions that you may have made 20 years ago. So a single repository, what we would call a product lifecycle management system, that just links all the data in a way that you can genuinely understand where it is and recover it. How did we make that decision? What was the input information? Why did we make that decision? What were the assumptions? Have the assumptions changed? Has knowledge changed since then? And you need to be able to go back sometimes decades in order to understand that. And your ability to do that in an accessible and robust way is massively enhanced with digital capability in the way that it wasn't in years gone by. We're going to have multiple partners on this sort of program. So are we all working on a single version of the product right the way through the supply chain? Pretty hard to do, but enabled through what we're talking about here. So the classic NASA hammer problem, what metric are we talking about? What unit are we talking about? You've got less potential for that if you apply these systems correctly. And you can control change better. We can understand better how what we actually build differs or matches what we designed, because they're never the same thing. So your ability to capture the as-built condition compared to the as-designed condition is important. You can feed in all the results and capture them and understand how the device changes in its performance through life. It supports you about validation and verification requirements. In other words, does the thing deliver the requirements that we set? It allows us to access the evidence base that supports safety cases. So when we talk to regulators and claim this thing is safe, and they say, well, where's your evidence and how did it all link together? If you properly manage this through a digital thread, then your ability to support the safety case is enhanced. It gives you that real baseline for managing your asset in service. And commercially, really importantly, if you put all that effort into designing it and you know where all the data is, then your ability to move from first of a kind to next of a kind is massively enabled. You don't have to start again. So if you get digital thread right, it can give you all of these things and more. And then at the end of it, if you're lucky, you can, in addition to what we call digital thread, produce a thing called digital twin. I've called it digital sibling here, thanks to some bright spark in another course at Oxford, who said, you'll never get a digital twin, that's too optimistic. So try for a digital sibling. So I thought I'll take that. They're right. So this is really an integrated model of how the whole plant works. So it's not the individual pockets of data and how we got to those decisions. It's a model, a dynamic model of how the whole thing works. And it enables that design optimization. And we've got a big question facing us, which is how the hell do you go about this? And the two ends of the paradigm are, do you aggregate the 100, 200, 400, 500 different individual models we've got and try and make some big behemoth model? Or do you try and find some black box approach to this? And it's probably more of the latter, but a bit of the former, and we've got to work that through. But we need to get to the point of having what we would term a flight simulator that represents the integrated performance of the plant. And that's the bit that high performance computing capacity is absolutely going to be essential for. I'll skip through the next bit, but this is just some of the applications and tools we use before I sort of come to some of the pitfalls. Just before I do that, here's the early stage design process that we're in. So we pinched a bit of the design process for this program from NASA. They use a basic paradigm called the concept maturity level, CML. And at the moment, we're sat somewhere between 3.5, that is an internal nomenclature, and 4. So over the last couple of years, we've postulated about 45 different designs of this thing, optimizing different parameters, deliberately stretching them to understand what we've got to trade to get the gain we want and get the balance we want. And the tool sets that we've used have allowed us to do that. They've allowed us to have reasonably high level models for those different 45 designs. So we can have a look at, this one's better on cost, that one's better on energy output, this one's better on fuel breeding. But not just this is better, how much do you have to give up on energy to get fuel breeding? How much do you have to give up on cost to get maintainability? So we deliberately pushed the design envelope to understand the trade space. And we couldn't have done that without integrated modeling capability that can spin through quite fast. And we're getting to the point by September this year when we'll have a basic single point design that we then optimize. So we've got some tools. We've got this integrated model called process that gives you a nice power balance, and as I say, allows us to optimize. It produces an outline cost estimate. The actual number is complete rubbish, but the relative numbers between the different solutions are really interesting. And we're evolving that in order to update it with new technology. You know, the original model was built with copper magnets. We now got to put high temperature superconducting magnets in there. And as I say, we've done over 45 whole plant concepts. We then have a really more specific model that we're evolving again, called what was called Blueprint, now Blue Mirror, that allows us to model the plasma. So this is a representation of the plasma that you saw earlier. These dots around it with the lines around them are magnetic field coils and magnetic field lines. And the bit in the middle that's colored is the plasma. So we can model the applications of that and optimize our magnetic coil placement, our neutronic analysis. Are we going to be able to breed the tritium we need from that? We've got all sorts of funky plasma models that are running at the moment, which then translate into what's the current demand and production from the machine. You know, what's the pulse look like? What's some of the temperature look like, bottom right? So there's an amazing amount of modeling capability, which is evolving all the time. And then we combine that with an absolute myriad of individual applications. So things about electromagnetics, the loads here, things about neutronics, diffusion of tritium into materials, as I said, computational fluid dynamics, all of that needs to be brought in together to allow you to do things like design components and then utilize code sets that on the same basic design. You can do a finite element analysis, you can look at its temperature performance, you can look at the diffusion of tritium in the components. So these great guys and girls at Culham at the moment are combining all sorts of applications that are commercially available, updating the basic platform with their own discrete capabilities and tweaking them for the fusion application. And it's really quite exciting what they're managing to do. And that's also allowing us to support what we call spatial integration. So this is an incredible design challenge. So how can we build the inboard bit of the machine? How can we support the forces and the loads in the structure and the facility that goes around the machine on the right? How do we lay out the whole plant? How do we do with robotic interventions? And this really interesting thing about it's not going to be people that maintain it. So you have to design it thinking about how a robot feels. How does the robot think about getting into the machine and out of the machine? Because it's not the same way that the human does. So digital capability is pretty fundamental. But I'll just come towards a conclusion now by saying it's not all upside. There are some pitfalls here. So the digital thread I've talked about, the systems, product lifecycle management systems, enterprise resource planning systems. Brilliant if you get it right. But implementing these sorts of systems is not an IT challenge, it's a business challenge. It's a cultural challenge. And you've got to be very, very careful when you do these sorts of things in large programs. In that, do you really want those electronic tool sets to support the way you want to work, or do you let them define the way you want to work? And if you don't think about that up front, you'll end up them defining the way you work. You need your culture in engineering and science to actually evolve to be able to operate those tool sets. And if you don't get that implementation right, it can drive years of delay. It can actually drive about 3 years worth of delay, to be accurate, in the transition between engineering, design, and manufacturing. So you really need to think about the implementation of these systems. It can also lead you to be a bit hubristic. So we can get into the paradigm where we say, well, we can't physically test this thing, so we'll model it, fine. And that will give us the answer, not fine. Because if we rely on the modeling, do we really understand in practice what's going on? Or are we just at risk of the computer says it's okay, so it's okay? And you can get into a situation in which you don't have an intuitive understanding of physics or the engineering because you're just looking at the computer screen. And that presents a risk to sensible engineering judgment. And I have found actually that if you don't pay attention to this, that there can be an over-reliance on the model at the expense of understanding what's genuinely going on inside the machine. And the big one, which is quite difficult to realize until you've actually seen it in practice, is that because you disaggregate information and are able to access it so easily, in a large program, you end up federating the design out to thousands of people. And that risks losing what we would previously have called the controlling mind. And if I go to one big fundamental reason why programs in the past used to take 6 years and now take 26 years, that's it. So I could ask, how did we ever manage without those tools in the past? And it's actually generally because we had small teams and people who understood the design intent top to bottom. There's quite an interesting quote from Elon Musk, who's an interesting character, but he says some good things. And one of the things he says is that he tries to ensure that everybody on SpaceX is the chief engineer. And what he doesn't mean by that is everybody gets an equal vote. What he does mean by it is that everyone in the program genuinely understands the problem top to bottom and all the trades. And as a result of that, they can work on their bit by fully understanding the context. And the larger your program gets, and the more you federate the tool sets, and the more you federate responsibility, the more you're at risk of people losing what the vision is. And then you're in trouble. So we used to exercise risk-based judgments on the evidence available within the constraints. And if you have an over-reliance culturally on digital tools and modeling, you risk losing that. So kind of in conclusion, I think it's critical to designing Fusion Plan. And it's critical to delivering major programs in a modern context. It supports well-framed program delivery, but it mustn't drive it. And if you follow this as a religion, it will drive cost and schedule massively. And it also needs a generation who can understand it and speak English, by which I mean, there's an awful lot of gobbledygook spoken about this. And sometimes you don't even understand the sentence that people have said. But if you get it right, it's really worth it. So one of the team that kind of jointly works between me and Andrew uses this in presentations. He says, well, look, you know, the problem we're trying to deal with in STEP and producing Fusion plant is like this transition. And remember that as you went from sail to steam turbines, you know, through into vessels in the 40s, you didn't really understand the physics and the science. And I said, no, Andrew, it's much, much worse than that. It's like going all the way to that, because it's not even the same physics above the water and below the water. It's a completely different problem as you scale up, and your ability to understand that and model it and synthesize it is really what you need to do. But I'll just remind you it's worth doing, because if we don't address that problem. Thank you. I hope that's helpful. I'm happy to take some questions.
I had one.
All right, small audience, no need for claps.
Large audience.
So I end my slideshow here. Yeah, let me end that.
Paul, thank you very, very much. That was fantastic. Great to hear we've got a question on the floor, so let's begin with you.
In my experience of digital thread in engineering solutions, one of the biggest problems to overcome is the commercial interests of your different software providers.
Absolutely.
None of them like to participate in integrating with the other tools that you want to. So
correct.
you get into a situation where you build integration and tend to lose some of the quality of the data as it passes through your thread.
Correct.
How do you manage that? How are you overcoming that?
Well, the first thing to say is I've caught a cold with that before, actually. I think the answer fundamentally is to try and look at open source nature of the technology. So the more technologically open and ideally commercially open that you can be on the base platform, the more likely you are to be able to transfer data with less risk of loss. It's not guaranteed, but we are just in a procurement process at the moment for a system, and we put an incredible amount of weight on openness, open standards, and the ability to transfer data, because as you know, irrespective of the state of technology at the start of a 25 to 30-year program, it's not going to be the same at the end. So we're going to go through several iterations of the relevant software platforms, because either the vendor will go out of business or they'll want to move on to the next iteration of the product. So you've got to accommodate that by trying to be as open as possible in the way that you set it up in the first instance. It's not a panacea, but you can get closer, I think, these days than we used to do in the past.
There are commercial products to integrate. In my experience, you always seem to trip over.
Yeah.
You know, where one supplier has not quite put everything you need in the in its integration interface.
No. That's absolutely, it's absolutely right. And you're going to always need to have effectively the capability to go and catch these things and sweep them up and reconcile. But I think we can get better at it. And I think there's some commercial mechanisms at the heart of the way that we're going to go about this, which actually bring partners together and encourage commercially collaboration to the greatest extent possible and insulate downside risk, rather than trying to load the risk onto the contractors. Because what we want here is partners for 25 to 30 years, not people who are in and out. We want people committed to this endeavour.
So they'll think they can do everything for you.
Yeah, this is the joy of trying to be, you know, what we call an intelligent customer. But you need to know that that's coming and then try to head it off. Yeah, daily battle.
Jeff, have we got any questions?
Yeah, there's some questions online. Can I take privilege and perhaps ask a question myself?
Go for it. Yeah,
I appreciate it's a big question, but maybe just focusing on digital technology that you're buying in. How are you dealing with the overall ownership of the end solution?
Yeah, so it's quite a challenge actually mapping who owns what even today.
Yeah.
So we have, I mean, I actually do chip in, Andrew, because you know as much, if not a lot more about this than me. But we have, for example, a lot of open source applications. So one of the ones I showed there is called Moose. So multi-physics, open-oriented simulation environment. That's actually an open source platform, but we've then strapped a load of applications on it. So by trying to use as much open source as possible, you can limit that problem. So what the IP concern becomes more about the data rather than the application itself.
Okay.
But inevitably, as we develop discrete applications which are very tailored to the problem set, we absolutely have to understand who started that, which organization, you know, actually holds the IP around that. At what point does it translate from something which was pretty open and everybody could use it to now somebody's actually got a claimable piece of intellectual property on it? So mapping that's quite hard. And then as you get to the sort of integrated stage at the end, we're going to have to put, we've got to walk a line here between encouraging the supply chain to get involved through allowing them to own intellectual property, because that is the ticket through this program to develop product for fusion enterprises across the world, whilst equally trying to maintain some control of some aspects of it so that we can develop the technology, or we can deal with suppliers who go bust or don't perform very well. So there's a massive data trade space on this. I think it's going to be a hell of a job just keeping track of it, frankly. Okay. So almost being able to manage the understanding of the data assets as well as use those assets is a difficult challenge in itself.
Yeah, absolutely. I mean, it's a massive multinational collaboration tackling fusion. It started off as competing countries trying to hold on to their intellectual property, and that very quickly went out the window. EAT's got some of the largest and most diametrically opposed countries working on it at the same time.
Really?
You know,
Well, this seems just conflict with the government strategy.
No, it's complementary actually. So there's this. We're at the stage of this technology where there are simultaneously international endeavours and domestic endeavours, and they're not at variance actually. So the UK is currently, although there is a potential threat to this, but it's currently participates in that in ITER, the International Science Experiment in France, by virtue of previously our membership of the European Union, we hope by associations and treaties. And actually, frankly, ITER, I think, will struggle to deliver without the UK as part of it because of our operational experience and supply chain experience. So we need to participate and collaborate internationally. But you get to any stage in a technology where you say, well, look, there's one path, which is the international path, but it's not mutually exclusive to having a bright idea yourself, like the Spherical Tokamak, and trying to pursue that, and not to pursue it to the exclusion of all else. We'll be pretty damn open with this, by the way. You know, relatively speaking, we'll be much more biased towards openness than closeness. And the reason I say that is that you can have a lot of turgid legalistic debate around IP, but what really matters is whether you've actually done it or not. So, you know, I give people the example of Hinkley Point C. So, well, look, I could give you the design and build manual for Hinkley Point C, the IKEA kit, and then so there's the Allen key and get on with it. It's meaningless, right? Unless you've actually had all of your team working together to understand how all that kit goes together, then the notional value of the intellectual property as defined in some sort of codified, you know, but so I think in practice we'll be quite open with lots of it, because where you really gain is in exercising the muscle of doing something. So I think they're not mutually exclusive, and I think we'll be relatively open, and that will probably limit the challenges we've got. But we'll see.
Chinese are really trying to.
Oh, well, they are. But the Chinese have got I mean, broadly speaking, they've got a twin track strategy. The fundamental strategy for the Chinese, he says, speaking for them, is their participation in ITER, through which they pay 9% in, but have access to 100% of the IP, is to take, and that's the same with all participants, apart from the EU, which pays 45%, but obviously has 27 members. Is that they will take the basis of the ITER design, make it larger and replicate it. That will get you, we would think, a viable fusion plant. We don't think it will get you a commercially viable fusion plant, which is why in the UK we've taken the track of trying to innovate a smaller device. So the Chinese will crack this problem by muscle and mass. They also do have some incredible scientists working on some cute ideas separately, but not as far ahead as we are on that. The Americans have finally woken up by virtue largely of what we've just started doing. So the White House announced what they call the decadal vision for fusion about a month and a half ago. And I say the White House, not the Department of Energy, it was White House driven. So each country, you know, the large countries are waking up to doing this themselves, but are also continue to participate internationally.
There's an analogy in space race as well, of course, that we're now in it's commercial now. SpaceX and others are at the point where they've got their commercial designs and their own intellectual property. We're much further back in that, and we're sharing as much as we can. But there's foreground and background IP, and as the commercial pathways develop,
Andrew, where the people might be able to hear you.
Yeah. So let's go. You had some questions from the remote audience.
Yeah. Okay. So Edmund has been waiting some time for his question, and you're probably a little biased in respect to the answer to this one. But is 2040 too late to reduce climate change? Wouldn't a very large number of smaller renewable solutions be more effective? So renewables.
Yeah. So no, and I'm not biased at all. I'm completely objective about this. So I think the answer is that we need literally everything. So is 2040 too late? We would like to be able to do this a damn sight earlier, but we have to be realistic about this technology. But if you reflect back on the energy production graph I showed near the beginning, the point really is that that does not stop in 2040 or 2050, that demand. It continues to rise. So we're very honest here. We say fusion is not going to be contributory to reducing the demand for fossil fuels realistically before about 2050. So we need to throw the kitchen sink at the climate change problem through everything, renewables included, in my view, existing nuclear, including small modular reactors as well. But I think what I was trying to articulate is all of that in and of itself will not address where we need to be by 2050, and it certainly won't address the demand after that. So the problem doesn't suddenly go away in the 2040, 50 or plus timeframe. So we need to continue to develop more. And if you think about two other aspects of the problem, one, the electrification of virtually everything needs energy to be provided to deal with it. The hydrogen economy, people talk about the hydrogen economy a lot. Hydrogen is just a mechanism of storing or transporting energy. It's not a production mechanism. So you still need to produce the energy to produce the hydrogen. And you can do that a lot more efficiently, by the way, through high temperature heat than you can through electrolysis. And there are some incredibly hard to decarbonize industrial processes where you need high grade heat, for which fusion is actually a really, really good source. So the answer, regrettably, is we need everything and we need it now. We'll go as fast as we can, but we definitely need this in the long run.
Okay. We've got another question online. I think you partially answered this, but I'll still ask the question because maybe you can extend the answer.
Sure.
Do you think keeping the single vision of general design means you stagnate the development and you miss opportunities? So
that's a really great question. So I think we're trying to implement, and I'm careful with the use of this word, but what you might term an agile approach in the design here. So we've iterated quite quickly to the design vision we've got now. And I say to the team that we have to drive that very fast, but we mustn't be myopic or emotionally wedded to it. So if we find that one aspect of that genuinely doesn't work, let's find that out really quickly. And let's have the ability and humility to pivot really rapidly to the next thing. So we don't run lots of multiple or backup plans because we don't have the capacity. But what we do is go as quickly as we can to say, is this going to work or not? And then to the next level of fidelity, is it continuing to work? Yes, keep going. And then if it doesn't, we pivot. And you need to set these programs up in a way that you're able to do that. That gets harder and harder as you get further into the design, both because the complexity level and the fidelity of data and volume goes up, but also because more and more people become involved in trying to pivot and adjust more people is just simply more difficult than a fewer number. One of the really tricky bits here will be the ability to accommodate evolving technology. So at some point, we've got to set some stakes in the ground. So I'll give one example of this. I've been very clear with the engineering team. You have to design this using the materials that we've got today or are going to be manufacturably realizable within the next 2 to 3 years. So we can adjust, mixes and manufacturing techniques in the near term, but you've got to design what you've got. Do not bring me a design that depends on unobtainium. However, we might find that unobtainium becomes available partway through the program. So at that point, we have to have a really good change control process, which says, look, we've pursued this element of the design with this material. We've now got this available. What's the relative benefit of introducing that change now? Is it worth the disruption for the performance gain, the safety gain, et cetera, because it doesn't gain you cost and schedule to change things. But is it better in the long run? Or do we keep going, get to our next demonstrated milestone, and then do a change afterwards? And actually, some of the things we learn in the submarine program are exactly that. The evolution of software and sensor capability is on a massively different cycle frequency than the evolution of turbine technology or nuclear reactor technology. And you can change the servers pretty quick, but you can't change the nuclear reactor. So some stuff you've got to go, that's it, that's fixed, we're done. Some stuff you have to positively enable late introduction and change. So do you have a policy of earliest feasible moment or last responsible moment? And these are programmatic choices we have to be able to make.
This must be one of the longest running engineering programs in history, isn't it?
Which one? The
There's the
fusion.
jet and fusion.
I suppose if you regarded it as a single program, yeah, it is.
I say that personal interest because my first job when I graduated was to work on the final analysis of the jet toroid
Right.
with Atkins. I'm retired now. So.
Well, I think actually that's probably testament to two things. Let's be positive on the first, which is the prescience of the designers that existed back in the 80s, Rabu and co, in order to produce a machine which is capable of a huge amount of adaptation, and it has had this. So it's had massive upgrade and change, but also the resilience. But it probably also speaks to the fact that maybe we should have been investing in doing something else before now as well.
So are there any other questions from people in the room?
Yeah.
Slightly lower level questions, high level.
Yeah.
Context, but going back to focusing on digital technologies.
Sure.
Obviously, safety is such a key part of the fusion industry. You
Yeah.
mentioned alarm principles and things like that. And in the system. Do you see digital as like a big enabler of the safety case and encouraging safety in it, and sort of what part do you see it playing?
So can I just, because
Yeah.
the microphones in this room aren't very good.
Okay,
so
shall I Sarah repeat that? Yeah, so the question is around the contribution of robotics, AI and so forth to safety case and maintaining safety. So the one word answer is yes. The slightly longer answer is there is a slight difference between delivering safety in a LARP and a safety case. And the reason I draw that distinction is we have to deal with being able to manage a very complex machine in which the technology is pretty new and we don't have a large evidence base to say that all the individual bits perform in the way we might understand. So from a safety case point of view, what we're probably going to do is our damnedest on the individual engineering, but we're also going to have to say, if it all goes wrong, don't worry, we're going to protect and contain the faults in the following way. Robots are clearly going to help us. So the first way they help us is that they minimize exposure, dose exposure to individuals. So by not having to put humans close to the machine to undertake diagnostic activities or maintenance activities, by using robots, we're immediately contributing to the ALARP principle. And our team in the robotic applications in challenging environment group, RACE, under Rob Buckingham at Culham, is doing exactly this. So they're working on robotic glove boxes now, actually not just for fusion, but to support decommissioning work at Sellafield, and indeed in Fukushima in Japan. They're supporting the decommissioning of the state of that plant, and actually who knows what's in it, and the robotics is going to help us. So by simply moving people away from the hazard, we're contributing to a lot. But you have to design the system really ideally in order to enable the use of robots. So robots are contributory. It's difficult at this stage, and I think we see this with autonomous vehicles, to be 100% confident about both the performance of those robots in reliability terms, but more important, the legal liability that comes with it. And that's an interesting set of challenges, which is why I come back to this distinction between safety and the safety case, which is you try and do everything you can to make the plant and the product safe. But from a regulatory point of view, you probably need to put a wrapper around it and say, even if all that doesn't work, we have a robust means of containing the hazard. And in our world, that means a sodding great containment building, which will simply mean that any accident scenario limits the exposure of people. So robotics is important, but so is the way that you design the whole plant to deliver safety.
So I would add that it should be self-evident from what we've heard, but in the fusion world, it's harder to get it going than it is for it to run away. So you're talking about chain reactions that you can get inefficient.
Yeah, the physics simply doesn't allow that to happen. But we do have what we call a radiological hazard.
How long does it take to die away? What's the half-life? If there is an explosion.
Well, so tritium, which is heavy hydrogen gas, if released, that's a half-life of 12.3 years.
Right.
But actually, the amount of it that you contain in the plant is really relatively limited in the device itself.
Okay.
So if you had a dispersal of that, it's, I mean, you know, compared to any fission fault sequence, it's just minuscule. It really is minuscule.
Sounding so
It's a
much
beta
so-
emitter, actually. So for those of you who are interested, you know, beta emitters are only hazardous if you ingest them, frankly. So,
Right.
you know, a decent piece of paper will kind of stop beta emitters. There are some waste issues to do with the activation of those metal components inside the device, but frankly, that's a matter of just a bit of time, distance, and shielding to manage them. There's no high-level waste in the way of, as Andrew said, fissile material,
Right.
or horrible unknowns as we deal with in Sellafield.
And that's one.
There's a couple of questions.
Did that
online.
answer your question? Did you have any supplementary questions?
I guess maybe it might be one separate question.
Yeah, let's go for it, yeah.
You sort of mentioned digital twins and digital
Yeah.
siblings. It's a bit of a buzzword at the moment.
Yeah.
I mean, you sounded maybe a bit dismissive of it. Do you see it as something that's useful? or
No,
do you see it as a buzzword?
I think it's really useful. I'm just cautioning that that all of the claims that are made around what, you know, an effective digital twin can do rely on just how close a twin it is and how easy it is to realize that representation of the physical components of device. And in this particular instance, the fact that there's so much uncertainty in the operation of each individual item means that being able to build a representative twin is a real stretch. I see this as an outcome of the project. So because we're on an empirical trajectory here, we need to try and build that model as we go. But the real gain comes when we've got the plant operating and we've then actually got something that we can benchmark. Correct. So yeah, so we can model all those sorts of bits. It's just the real trouble is, I mean, the fundamental problem is that the behavior of plasma is bloody uncertain. And the knock-on effect of that on everything else. So you can be really effective and high fidelity about your finite element analysis modeling of, you know, a magnetic limb, for example. But the way in which the plasma oscillates and may have destructive events that then cascades onto that is very uncertain. So some aspects of this you can box down and say, I really know what's going on here. But if the fundamental driving force behind all this is extremely uncertain, then the propagation of those uncertainties is difficult, which is why I say it's an aggregate uncertainty quantification problem. So you can theoretically say, oh, I'll build all this up and I'll have some sort of amazing integrated, all singing, all dancing. You know, I sometimes say the NHS IT system, for those that were, you know, old enough to remember the attempt to do that. So I think we'll get there, but we won't really know until we've built the machine and then try and build a model that coexists with it. And so I see it as an outcome of the program rather than necessarily as a full input to the program. So I'm fully in favour of it. I'm just not sort of not caught up by the religion of it.
Thank you.
The good question.
Jeff?
Okay. What role is, this is a question from Praveen. What role is AI going to play in the evolution of models and solving the problems? And are the engineers trained in these cutting edge technologies?
I can have a, I mean, do you want to have a go at that?
Well, so yes and no. It's a simple answer. There's a massive investment going into machine learning and artificial intelligence in all our programs. So at UKEA, we've taken the view that AI and robotics are going to be fundamental to the future of fusion development. And so some of those robotics things you've seen are great successes from our race department, but there's also heavy investment in autonomous vehicles. So we're one of the test sites for autonomous vehicles. Now you might ask, well, why are we doing that? What's that got to do with fusion? And it's exactly because of that AI machine learning. So we're developing learning our skills on things that are applicable in the autonomous vehicle world. And we're kicking off a massive digital program to invest in AI machine learning underlying our modeling capability as well.
It does, to go into one really technical example, it does offer a huge potential though. So I said earlier that the behavior of plasma is extremely uncertain. and you can theoretically model the progression of what we would call disruptions. But they happen on an incredibly fast timescale. And it's very difficult for human analysis to pick up what's happening in the early stages of those disruptive events and the precursors to them. But actually, by using machine learning to go back across the extensive database of operation of JET, for example, there is the potential for machine learning to start to pick up, knowing that a disruption occurred and it had the following characteristics, to start to look for what the precursors were. And that might have the ability to start to offer in sensing of the early stages of a problem to then feed into control system design to mitigate those events before they get to that stage. So there's amazing what you learn talking to Fernanda, but so you know, there is an application for AI. There's lots of applications for AI here.
So thank you.
Any more questions from the?
Yeah. Can you capture the heat from a fusion plant and utilize it?
Well, that's the aim. That's the whole aim. We've produced all this heat. It's high grade heat. We've got to turn it into something.
Yeah.
So the answer is yes, we can. The basic way of doing that, is the energy in the neutrons hits this lithium blanket, which does two things. One, it breeds the tritium to keep the fuel going. But actually what it also does is heat up the lithium, and it heats up what we call the first wall of the machine, the protective wall inside. And we pass coolant through channels in that lithium blanket, or molten lithium coolant, and through channels which sit behind that first physical metal wall, usually made of tungsten. And so the water or the helium gas or the liquid lithium, some coolant medium, we pump through, and that goes into a heat exchanger. And then from that heat exchanger, you then can do some traditional things like run steam cycle, or maybe some fancy things in the future, like running a supercritical CO2 Brayton cycle. So that's how you do it. And actually that bit, particularly the steam bit, we know how to do that. So I hang on to that. Because I say to the engineering team who are off on, oh, we could do this and this and this. I said, look, can we just have one thing in the program that we genuinely know how to do that's not that risky, please? And like, and an old submariner that me actually understands as well. So.
Okay, so that's what you determined to be the waste heat, effectively.
Well, no, that's the heat we use to generate the electricity.
Literally. Okay.
Yeah, so you have to take the heat you extract and then do something with it. Heat conversion is actually dreadfully inefficient. So, you know, one of the problems with all this is that, you know, you can generate enormous amounts of thermal energy. Your then conversion to electrical energy at the end of it doesn't look that great. But that's the same in fission at the moment. You know? So yeah, so high grade heat or combined heat and power. All sorts of applications that we can. But yeah, at the end of the day, the bog standard way of doing this is stick a steam generator and a turbo generator set on the end of it.
So I'm mindful of time. We've got about 5 minutes left. How many more questions have you got online? Does anybody else in the audience?
That was the last one online.
So we give the last question to.
Yeah.
Well, it was really thinking about the evolution of the fission side of things.
Yeah.
Moving towards the small modular reactors.
Right.
Is there anything equivalent on the fusion side of things?
Yeah. So the first thing I would say is what we're trying to do with STEP is to be avowedly small. Now, everything I've described doesn't sound small, but compared to the traditional Tokamak evolution in ITER and then the European program known as DEMO beyond that, I mean, we're about a third of the size of that. So small, relatively, yes, we think the spherical tokamak is the approach to that. Modular, yes. So although this is a prototype that we're doing, we're trying to go about the design of the prototype in a way that sets up the major items and configuration in a way that leads to modularization when we go to commercial. So what you might call platform-based design if you're an automotive or a similar sector. And the real innovation that Rolls-Royce have made in the small modular reactors program, apart from the design basis which comes from the submarine program, is actually, which is why it's going to work, is I mean, it genuinely is. It's like zero risk of not working this. So the innovation is to produce the design in a way that the thing is manufacturable in a factory, and you can do many off. And that both drops the cost, but it also massively increases the quality, because if you can control your conditions and replicate, then your quality standards are higher. Therefore, that supports your safety argument fundamentally, and your cost reduction, and so on and so forth. And our approach to this, although we're doing a prototype, is to think about architecting the design such that we can move into that in that direction. So modularity is important, and we'll try and design the thing so that the vast majority of it is able to be factory manufactured and shipped and assembled there with pre-testing done, rather than trying to assemble everything on a construction site. So yes.
Thank you very much. So I'll draw things to a close. So thank you everybody in the room, and thank you everybody remotely as well. If we can just thank Paul with a round of applause.
It's not boring talking about it, I have to say.
Fantastic.
Great, thank you very much.